Hello, welcome back. I am Francesco Orabona, and this is the second part of the parameter-free online optimization tutorial. In this part, we will actually explain you a parameter-free convex optimization procedure. Now, remember what we did in the previous part. We saw why tuning learning rate is difficult. In particular, the key quantity is this distance between the initial solution and the optimal one that is unknown, and it cannot be easily estimated. So the only thing that we can aim for is a convergence rate of this form, where you have to pay this additional term because you don't have this information. So what's next? Here we will show you how to obtain this convergence rate without tuning anything with a new algorithm that is not stochastic gradient descent. Now, before showing you the solution that we prefer, let me show you different solutions that you might think. So the first one is how somebody from optimization would approach this problem, and in particular, how Nemirovsky would solve it. And I know about it because I asked him in 2013. Remember, the idea is that you have a bunch of learning rates, and you would like to try all of them in order to discover the right one, but if you do it, it will take forever. So you have to find a way to try all the learning rates with the same complexity as trying just one. How can we do it? We can allocate a different budget to each learning rate in a very smart way. And so in particular, let's call the procedure M of alpha and capital T, running gradient descent for capital T iterations with the step size eta t that is equal to alpha divided by square root of capital T divided by the norm of the gradient itself. Now, this normalization here is exactly to make the learning rates independent from the Lipschitz constant from the scale. You start from the origin and you return the average of your iterate. Now, what you do is that you run this procedure with different value of alpha from 1, 2, 4, 8 till 2 to the n for t equal to 2 to the n iteration for each one of them. And you run this thing one by one. Then when you arrive at the end, you return the one that has the smallest value of the function f. Okay? Now, what you're doing here is basically you are trying all the possible learning rates and setting alpha each time to a different value. Now, there is one alpha that will be the right one. What is the right alpha? The right alpha will be the one that is roughly the norm of the optimal solution because we start from 0. So set m such that the norm of the optimal solution is between 2 to the m minus 1 and 2 to the m. Okay, here we are assuming that the norm of the optimal solution is bigger than 1 for simplicity. This means that for any batch n bigger than m, you will produce a solution that has accuracy, Lipschitz constant, norm of the optimal solution, 2 to the minus n divided by 2. And you get this thing every time you run the procedure with alpha equal 2 to the m for t equal to 2 to the n iterations. Now, this is the right thing to run, but this is not the only procedure that you were running. You were running a bunch of all other stuff before running this one. So how long does it take to complete this entire thing? So the total number of steps from the beginning till executing the batch number n will be of the order of n2 to the n. So if you put everything together, this means that if the total number of iteration is big enough compared to the norm of the optimal solution, this entire procedure will have the same complexity as using one learning rate, but will return you the optimal convergence rate up to multiplicative factors. Now, this is a fantastic construction because it tells us a very important message. The message is the problem that we are trying to solve, it's possible, it's solvable, at least in the batch setting. However, as Nemirovsky admitted, this does not work in the stochastic setting. The reason is that among all the runs that you do with different alphas, there is one that is the right one. But in order to understand which one is the right one, you have to calculate the argmin over f for all the solution that you generated. But if you cannot calculate the argmin, because you are in the stochastic setting, you don't know anymore which one is the good one, and you don't know how to proceed. Also, there are also another couple of problems. You waste a lot of computation here, trying a lot of different learning rates that are basically the wrong ones. And also, this is not something that works in practice. I mean, again, this is a theoretical construction that tells us that the problem is solvable. It's not something that you want to implement. So let's move to another solution that is a little bit better. We might think to use what in online learning we call a doubling trick. What is a doubling trick? In online learning, every time there is a parameter that depends on unknown quantities, depends, for example, on things that are in the future, and you don't know how to tune it optimally, what you do is that you start from some arbitrary setting. Okay, so here it's a learning rate, you start from eta 0. Then you run your algorithm, so you done stochastic gradient descent in our case, so you output x of t, you get the gradient, then you check a condition. The condition says, is this learning rate that you're using still good in a certain sense? If yes, keep it and just do your update step. If not, reset everything. Start again from 0, double your learning rate, and then start again optimizing. Now, this solution is a little bit better than before because this procedure now works in the stochastic and online setting. However, there are a couple of problems. The first one is that when you analyze this algorithm, the bound is actually suboptimal. Also, this is not something that you actually want to use. Again, it's not a practical algorithm. Every time there is a doubling trick in general, it's not really an algorithm that you want to run. Because every time you are doubling the learning rate, you're starting from 0. You're basically forgetting everything that you did till this moment. It's not a practical algorithm. The last reason is that understanding why this is the right thing to monitor, here you're basically monitoring the gradient multiplied by the iterates, and the moment that they become too big, the sum of them becomes too big, respect to the learning rates multiplied by the total number of iterations, you have to reset. Where this condition comes from. It turns out that understanding why you have to do this is as difficult as designing and analyzing the optimal algorithm. So there is actually really no reason to use this suboptimal construction here. But again, the message here is that, yes, the problem that we are trying to solve, it's possible, even in the stochastic setting. Another alternative is looking at all the learning rates that you want to try and saying, instead of trying them one by one, I want to try them all at the same time. So I have a bunch of stochastic gradient descent procedures, and you can show that you just need a logarithmic number of them in the total number of iterations. And each one of them has a different learning rate. And you run them all of them at the same time, and you have a way to fuse all the iterates generated by all these different procedures, so that in the end you have just one iterate in each step. Because otherwise you would have to query a lot of gradients. In this way, you just query one gradient. And then you pass surrogate gradients to these procedures. Now, a bunch of different approaches has been proposed in the literature, depending on what is the procedure here that you use. You don't have to use stochastic gradient descent. You can use something even more complex than that. So in this sense, this approach is extremely general. However, it's still a little bit cumbersome because you're still running a lot of algorithms. And it's true that if you have a lot of computers in which you can run these procedures in parallel, you might say, okay, at the end of the day, I'm not really, this entire procedure is as fast as running just one algorithm. But it still feels a little bit unsatisfying because, again, you're wasting computation, maybe parallel computation, but still computation on learning rates that are not the right ones. So let me show you the fourth alternative, that is something that actually works. It doesn't waste anything. So the idea is that you start from the convergence rate that you would like to obtain, and then you look at the corresponding regret guarantee, okay? In the sense that if you have this regret guarantee with respect to any u, then if you do the online to stochastic conversion, you go back exactly to this convergence guarantee. Now, you look at this convergence this regret guarantee here, and you might say, I might try to use a follow the regularized leader procedure in which this quantity here is exactly my regularizer. And this is the regularizer that you choose. You see that is a regularizer that is changing over time, and it must change over time. You cannot use a constant regularizer. And so you would have this kind of update in each step. Now, I want to stress that I write the update as an argmin because this is the standard way to write follow the regularized leader updates. But this has a closed formula, so you don't have actually to solve an optimization problem in each step. This is as expensive as doing one iteration of stochastic gradient descent. And by the way, follow the regularized leader is exactly the same as regularized dual averaging. It's just different names for different community, depending if it is online learning or optimization. Now, this algorithm actually works very well, but it's very difficult to explain why it works. And it's also very difficult to analyze because this regularizer here, it's not strongly convex. So the analysis is not the usual one. So instead of explaining you this approach, we will explain you another approach that is this coin betting view. Now, let me stress the fact that this is exactly the same approach than FTRL that I just showed you. It's just a different view of the same algorithm. That makes everything easy. The analysis will become very easy. The intuition will become easy as well. It works extremely well, even better than the one before, and gives a new interpretation of optimization as something related to gambling and compression that it might be interesting on its own. Now, the caveat here is that this is very different from the usual optimization algorithms that you know. So in the next slide, I will explain you the intuition behind this approach. And in order to understand it, really try to forget everything that you know about gradient descent. Try to forget about the fact that you're going through in the direction of the gradient because the function is minimized in that direction. Forget that, okay? It might be better to forget everything that you know about gradient descent and try to learn this new, completely different view of optimization. Okay, so what is betting on a coin? You start with $1, and basically it's a game. You basically bet money on the outcome of a coin. Now, we will code the coin as a -1 and a +1, the two sides of the coin. And the money that you bet, they also have a sign, because if they are positive, you are betting on the positive sign. If they are negative, you are betting on the negative sign. So if I say that for example, I bet -50 cents, this means that I want to bet 50 cents on the negative side of the coin. And so we can write that wealth will basically be updated in this additive way, so that if the money that I bet and the coin have the same sign, I'm winning money. If they have different sign, I'm losing money. Now, there is only one rule. You cannot borrow money. And what's the aim of the game? You have to win as much money as possible. Now, it turns out that this is a classic problem. It was solved for the first time by Kelly with the Kelly betting criterion, that it says the following. You should assume two things. You should assume that the coin is stochastic, and you should assume that you know the bias of the coin. If you are in this situation, the optimal strategy, in the sense that any other strategy asymptotically will do worse, is to bet 2 times the bias of the coin -1 fraction of the money that you have in each round on the side that is appearing more often. And by the way, the fraction of the money will be always in blue, the money always in gray. So let's say that, for example, the coin is not fair, but it's very close to a fair coin. The bias is 0.51. You should bet 2% of the money that you have blindly, doesn't matter if you win or lose, always on the same side. Now, if you do that, Kelly proved that the expected log wealth will increase linearly in time. So roughly speaking, you can imagine that your money will increase exponentially over time. Now, making an exponential amount of money seems great, but we are assuming two things that are very strong. We are assuming that the coin is stochastic, and we know the bias of the coin. Let's remove assumptions. First assumption, let's remove the fact that the coin is stochastic. The coin is non-stochastic. It's an arbitrary sequence, even adversarial, of outcomes +1 and -1. And you still want to bet a fixed fraction of money in each round. What is the optimal fraction? Now, this is a very simple one-dimensional problem that you can solve just with the derivative. And you get that the optimal signed fraction of money is the sum of the outcome of the coins over the entire game divided by the number of rounds. Okay, and so you bet in each round this number here that remember as a sign, because it tells you on which side you should bet, multiplied by the current money. If you do that, your money will increase exponentially over time. And now it will increase deterministically. There is nothing stochastic here anymore. That's great. We removed an assumption, but we are still assuming something strong. We are still assuming that we know the future. Here, knowing this quantity means that you know in advance how many heads and how many tails there will be in the entire sequence. You don't have to know when they appear, but you have to know their number. It's a very strong assumption to make. Let's remove even this one. If we don't know the future, what do? We could use, there are many strategies, but the simplest one is to use what is called Francesco-Trofimov better. Now, Francesco-Trofimov better basically says, in each round, we estimate the probability, and probability in quotes, because nothing is stochastic here, everything is deterministic. So this is just a number between 0 and 1, it's not a probability. So the probability of heads, let's say that heads is the one that is appearing more often, in the past. So what you do is that you count the number of heads in the past, you add 1/2, and you divide it by number of rounds plus 1. Okay, so this is your estimate of the probability. And now you still use a Kelly betting approach. You bet twice this fraction minus 1 fraction of the money in each round. So in our case, this becomes that you have to take the sum of the coins in the past and divide it by number of rounds plus 1. Now you see that everything is known in this formula here. And if you do that, now the amount of money that you make will increase exponentially over time, but you will pay this polynomial factor here. And by the way, the exponential factor is exactly the same as before of the previous slide. So this means that you are winning as much money as you knew in advance how many heads and how many tails there are in the entire sequence. But now you don't have to do anything. You don't have to assume that you know stuff. You don't have to tune any parameter in the algorithms. Everything is completely automatic. And the only price that you pay is this 2 times square root of t. That is polynomial with respect to an exponential amount of money that you make. So basically you pay nothing for it. So this means that you can always win tons of money every time the coin is biased towards one side without assuming anything. Again, there is no stochasticity. The outcomes of the coin can be decided in any way. And the entire procedure does not have any parameter, learning rate, regularizer, prior, or whatever that you have to tune. So why this is interesting? What is the connection between this and optimization? Now, this is the most important slide here. I will show you in 2 lines of proof that you can always reduce optimization to betting. So this means that you can use a parameter-free betting procedure that guarantees you an optimal amount of money, and you can transform it into an optimization algorithm that will be parameter-free and will give you optimal conversion rate. Now, you don't have to use Francesco-Trofimov. You can use any optimization on any betting algorithm you like. The only thing that we need is that it guarantees you that the amount of money that you make is some function h of the sum of the coins. So for example, for Francesco-Trofimov, you get that the function h is this exponential function here. Now, let's say that we want to minimize the function absolute value of x minus 10. Now, this is the most important line here. This is the reduction. Every time the betting strategy tells you to bet money with a sign, that is the x in which you query the gradient. You take the gradient, you flip the sign, that is the coin. If you know how much money you were betting on which side and you know the coin, now you know if you win or lose money. You pass this information to the betting strategy. The betting strategy tells you what is the amount of money that you should bet in the next round, and that is the next x of t. That's it. This is the entire reduction. Now, My claim is the following. The average of the bets will converge to the minimum of the function. Not only that, the better is your betting algorithm making money, the faster you will converge. Okay, let's prove it. The function in the average of the bets must converge to the function in the optimum. So first, Jensen inequality, because this is a convex function. Then again, convexity, definition of gradients, and the definition of the coin. Now, look at this quantity here. X of t is the point that we query, but it's also the gradient. It's also the amount of money that we bet. Ct is the coin. So the sum of Ctxt is how much money we won or lost throughout the entire game. So this means that this quantity here is lower bounded by this function h. So we lower bound it by the function h and the initial dollar. Now you look at here, and there is some of the Ct here, some of the Ct here. We just remove them and we upper bound with a maximum over v. Now, if you look at this quantity here, this is nothing else by definition of the Frenchel conjugate of the function h in x star. So that's it, we proved it. The average of the bets will converge. Not only that, the faster is the growth rate of the function h, the smaller will be the growth rate of the function h star. So now this immediately implies that we can use Krzyzewski-Trofimov to do optimization, as it is. We just need a function that is one-dimensional and the gradients are just exactly +1 or -1. So this is the amount of money that Krzyzewski-Trofimov tells us to bet. That is exactly the x of t that we play in each round. And is the sum of the coins in the past divided by number of rounds +1 multiplied by the wealth. Coins is equal minus gradient. Wealth is equal initial dollar. And the amount of money that we win or lose throughout the entire game, that is x multiplied by the coin minus gradient. That's it. This is your order. Now look at it for a second. This is not stochastic gradient descent. Do not try to interpret this as stochastic gradient descent because it's not stochastic gradient descent. But it's as simple as stochastic gradient descent. If you can implement stochastic gradient descent, you can also implement this algorithm. Now, the 2 lines of proof that we did before immediately imply a learning rate, a convergence rate for this algorithm. We just have to calculate the Frenchel conjugate of that exponential function, and we get this convergence rate. Now, everything seems good, but this is one-dimensional. The gradients are just +1 or -1. It seems a toy algorithm. But actually, we can use it for any function that is 1 Lipschitz in any number of dimensions, even infinite. It doesn't have to be 1 Lipschitz, by the way. I mean, it has to be any Lipschitz. You just have to know the Lipschitz constant. And the algorithm is exactly the same. The only thing that you change is that the multiplication here becomes an inner product. And in the convergence rate, the norm will appear. Now, why this is a good convergence rate? Apart from the fact that it matches the lower bound, fine. But let's rewrite it in a different way. Let's rewrite it as the minimum over alpha of this quantity here. If you solve for alpha, you get exactly the same bound as before, okay? So this is just a different way to write the convergence rate. Alpha is not a parameter of the algorithm. And compare it to the convergence rate of gradient descent with alpha divided by square root of t learning rate. They're exactly the same thing. The only difference is that alpha here, it's a parameter. You have to tune it. If you don't tune it, the algorithm won't work. Here, instead, in this algorithm, alpha is not a parameter. But somehow you get always the performance as if you tuned the learning rate in stochastic gradient descent. You have to pay a price for this adaptivity, and the logarithmic term is exactly the price that you pay, that from the lower bound, we know it's tight. Now, apart from the formula, let me show you what this algorithm is doing on a real function. Now, first round, Krzyzewski-Trofimov in the first round tells us bet 0 money because there is no past. So money equal point that we query, first point x equal to 0. So we are here. We query the gradient. The gradient is -1. Coin is equal to minus gradient. So the first coin is a +1. So in the second round, Krzyzewski-Trofimov tells us of the $1 that we have, bet 50 cents on the coin 1. You bet it, you win, because this is exactly the gradient that you get in this point. And you keep winning, because you are always betting on the same coin or gradient. And given that you keep winning, your amount of money will increase exponentially over time. And this means that you go exponentially fast from the initial point towards the optimum. Now, at a certain point, you will jump on the other side of the function. So here, you are still betting on observing this gradient, and instead you observe this other gradient. This means that you will lose a lot of money, because remember, that money that you bet is equal points that you query. So this means that if you don't have a lot of money, the next x has to be small. And so you automatically backtrack. And then the algorithm again will start converging here. And at a certain point, the algorithm will basically oscillate around the optimum and then finally will converge. So if you look at this thing, this is very different from all the other strategies that people usually suggest. People say you should use a constant learning rate, or you should use a decreasing learning rate. This approach instead says, no. Go as fast as you can. Go exponentially fast in the interesting area. And then once you are there, then you can start decreasing your learning rate. And this is somehow the optimal thing to do. When you are far, learning rates have to be really big. When you are close to the optimal, learning rates really small. But given that you don't know how far is the optimum, you cannot really implement this strategy. But somehow this betting approach is implementing this strategy and is achieving it without estimating exactly where is the optimum each time. Now, the only thing that I want to say, the last thing that I want to say is that we didn't code this strategy. There was never a moment in which we explicitly said, okay, this is the right thing and we want this in our optimization algorithm. We just realized that the algorithm was doing this thing after we designed it. And somehow, given that the algorithm has the optimal convergence rate, it has to do the right thing. Now, let me show you another example of a betting algorithm. We say that the optimal learning rate is something like the norm of the optimal solution divided by square root of t, where you start from 0. Now, you don't know the optimal solution, but you might think to approximate it with xt. Okay, when you're close to the optimum, these two things should be more or less the same. And use a constant learning rate here so that stochastic gradient descent becomes something like this. You rescale the gradient by the norm of xt. And it turns out that this was an heuristic proposed in deep learning optimization papers. Now, it's clear that this cannot really be the right update, because if you start from 0, you don't move from 0. But still, it might be good enough that it might be worth analyzing it. And plus, it seems to work pretty well in practice. So if you try to analyze this thing from an optimization point of view, it might be really difficult. Let's try to use a coin betting point of view. What you do is that you say, I bet a constant fraction of my money, 1 over square root of big T. And so in each round, you bet 1 over square root of t multiplied by the wealth. Now, x of t, it's always positive in this way, by the way. The wealth is always updated in this additive way. And so given that we bet in this way, it's also updated in this multiplicative way. So this means that the next x of t plus 1 is equal to 1 over square root of t for the current wealth. The current wealth can be written in this way. And then this means that you update x of t plus 1 as the previous x of t minus x of t divided by square root of t gt. Now, these two updates are exactly the same. Here, the norm is missing, but we are in one dimension, and x is always positive. So these are exactly the same thing when you go to positive side 1D. Now, this is a betting algorithm. Can we show that this converges as an optimization algorithm? Yes, in 2 lines. We take the wealth, that is a closed formula. You lower bound it in this way so that you have a function of g. You calculate the Fenchel conjugate, you get a convergence rate. That's it, immediately. And if you look at this convergence rate, this is almost the optimal convergence rate. Only the square root of log is missing. And the only other caveat is that x star has to be positive, because it's very natural. The algorithm is always predicting something positive, so it makes sense that this is positive. But apart from that, this is the first explanation that this kind of algorithms make sense, at least in this restricted setting. Then Ashok will tell you something more about the connection between parameter-free algorithm and these kind of updates in a more general way. Now, the last thing that I want to tell you is that everything was 1D because we have a coin. But I also told you that you can go from 1D to R to the D. In the case of Francesco trophium, just removing multiplication and substituting with inner products. But this is true only under certain technical conditions that are satisfied for Francesco trophium. It might not be satisfied in general. Another way to go to D dimension is that you put a coin on each coordinate. And this immediately gives you something, an Adagrad style kind of algorithm that always works. You don't need any condition. This is always giving you a convergence rate. The last thing that I want to show you is that you can decompose learning x of t, optimizing x of t in two pieces. You can optimize the magnitude, that is a 1D problem, and the direction, that is a D problem, but an easy one. Let's see how to do it. You have two algorithms. One is the 1D one, and this is learning the magnitude. Instead, this is learning the direction. And it's basically doing optimization of a unitary ball in R to the T. Now, it works that basically in each time step, you get the both prediction from the 1D algorithm and from the direction algorithm, and then you compose x of t just with the multiplication of the two. Then you receive your gradient, you pass the gradient as it is to the direction learner, and then you pass the inner product between the gradient and the direction to get a number for the 1D learner. Now, it's easy to show, and I won't go through the steps because these are all equalities, that the regret of this entire procedure turns out to be the regret of the 1D learner over the norm of the optimal solution, plus the norm of the optimal solution multiplied by the regret of the direction learner over the direction of the optimal solution. Now, why this is good? Because the direction learner is an easy problem. It's easy because it's bounded. You're doing optimization in a bounded domain. Every time you're in a bounded domain, remember we said it in the part 1, the tuning learning rate, it's easy because you can upper bound everything by the diameter of the domain. And so tuning learning rate here, there, super easy. And so for this part, you can use just projected stochastic gradient descent with learning rate tuned with the diameter. For this part instead, you need an algorithm that is parameter-free, but 1D. And here, use coin betting. And that's it. You can always reduce any optimization problem to two algorithms, a coin betting algorithm and a projected stochastic gradient descent algorithm. So to summarize, in this part, I try to explain to you that removing learning rate is possible. You should not try to tune them. You should just remove them completely. And also I showed you this idea of coin betting, that and a particular algorithm that allows you to win an exponential amount of money on a non-stochastic coin with a parameter-free algorithm. Now, given that you can reduce optimization to betting on a coin, this implies that you can transform any betting algorithm into a parameter-free optimization algorithm. Now, in the next section, Ashok will show you a lot of consequences of this simple idea, how you can adapt, for example, to strong convexity or to smoothness. Again, everything going back into a coin. So that's it. Thanks for your attention.